If we were to add or subtract electrons from this atom, you'd expect that its radius is going to change. You'd probably expect that as we take away electrons, it's going to get smaller. And as we give it additional electrons to make it a minus charge, we expect that it's going to get bigger. And that is a completely logical approach and is borne out by what we actually see in evidence. So our cations, keep in mind our terminology, cations, positive charge, they're going to be smaller than our parent ion. And you can see that down here in this table. Our gray atoms are our neutral atoms. The pink piece is the charge state. And now in all these cases, they're ending up being isoelectronic with the noble gas. We'll come back to that word in just a minute. Basically, we're saying that we end up looking like the noble gas. Now, if we were to give it additional electrons, and you see that happening over here, we start out with the neutral, we give it some electrons, the radius increases pretty dramatically there. So our anions are going to be larger when we do ionic radii. Now, as you go down a group, we're going to be adding more and more electrons. So if you stay with the same charge state, +1, +1, +1, you do expect that they're going to follow the same trend we saw for the atoms. As you go down, they get larger. And that's exactly the case. Similarly, ion sizes are going to decrease across a period, going from left to right, for the same charge state. Now things get much more complicated if we're trying to compare different charge states. Now we're going to actually have to think about a lot of things simultaneously. Notice that we're at +1, +2, +3, -2, -1. So we're going to have some differences there. We can't really do a direct comparison between what we see happen for the cations and what we see happen for the anions. Best is to compare them directly to the neutral atom whenever possible. Now, a little bit more information about some atomic radii and ionic radii. Now, if the same atom starts losing additional electrons, it's going to get smaller and smaller. If we come back to the previous slide for a moment, that means that our boron, when it becomes boron +1, it's going to get smaller, but not as small as B3+. B+ becoming B2+, it's going to get smaller still, and finally it's going to get down to this size by taking away that third electron. But there's going to be a couple of waypoints along the way. It's just that our triple plus ends up being the really stable version of this atom. Similarly, lithium, it's going to be most stable as a +1, along with everything else in its group. Everything in group 2 is going to be pretty stable as a +2. Our group 3s are going to be stable as +3s. Our 6s are going to be stable as a -2. And our group 7s are going to end up being stable as a -1, along with being in their neutral state. Now, the term isoelectronic means that it has the same outer electrons. Now, depending on what source you're looking at, you may have different definitions for valence electrons. Some books will specify that valence electrons are all of the outermost s and p orbital, but that's it. So you'd have it cap out somewhere in the calculation of 0 to 8. Other books will also include the outermost d orbital if you're in the transition metals. But there's some distinctions that are made there and some differences that are existing there. I think the best way to approach isoelectronic, though, is to focus on the s orbitals and the p orbitals. If you have the same configuration for multiple atoms or ions, when you pay attention only to their outermost s and p orbitals, they're going to be isoelectronic. Now, that's a little hard to follow. Let's see an example that should help with that. Now, this is going to be oxygen double minus, fluoride, F minus, neon, sodium, magnesium 2+, and aluminum triple plus. All of these are going to end up having the same outer shell electrons. Let me show you why. So you see here a periodic table. Now, if we have oxygen, we have a 1s2, 2s2, 2p4. If we get it to be the -2, we add 2 more electrons, and we'll have a 2s2, 2p6. For fluorine, 2s2, 2p5, give it an additional electron, it's now 2p6. Neon was already 2s2, 2p6. With sodium, we're at 2s2, 2p6, 3s1, but we take away the outermost electron to make it the +1, the 3s1 electron, and it ends up having the same configuration. So you see that all three of these, if I keep going along, they're all going to end up having 1s2, 2s2, 2p6. Isoelectronic. Now, if we're looking at isoelectronic atoms, Notice that we have the same number of electrons in the same places. The only thing that's different is the number of plus charges in the center. So with the isoelectronic species, the one that has the most plus charge is going to pull those number of electrons in tighter, right? So the heavier atom, the bigger atom in your mind, is actually going to be the smaller ion, because it has enough plus charges to pull every one of those electrons as tight as possible, as opposed to the ones that had less plus charge. They can't pull the electrons in quite as tightly, so they're going to be a bigger radius.